Hi, I'm Jaden and I'm here to present the spool on the truck problem. It's just me working alone on the report and presentation right now. So what is the problem? So the problem consists of a spool of sheet metal on the truck that is not secured with the ropes when the truck is accelerating. And when the truck accelerates, the spool should roll off the truck, assuming that there is no slipping. But what is no slipping? Will you ask? No slipping is just telling us that the object has a firm contact with the surface, so it should not slide. So when the truck accelerate, the spool should not slide and slip. And we also try to find the angular. So this problem consists of the spool trying to find the angular acceleration of the spool and the acceleration of the translation and the normal force as well, but we mainly focus on the angular acceleration of the spool. So pretty much this is just me solving it. This is the free body diagram. As you can see, there's a normal force, a friction force acting on it, and I made this body diagram into this, and there is a moment of inertia acting on it while it is rolling. So that will be our angular velocity. And first I find the normal force, which is just mass times gravity. So 500 times 9.81 gave us 4,905 newtons. And then I went straight to finding the angular acceleration, which is just, as you can see on the free body diagram, that the moment of inertia is acting on it. So I just solved that through the radius squared times the mass, and I'm able to get 3 rads per second squared for the angular acceleration. Then I try to find the normal acceleration, which is seen below, which is just 1.5 meters per second, and then the friction force, because it's also acting upon this free body diagram, which is just 750 newtons. So how did I get this? I got this, sorry, and I checked this with MATLAB, and then the file that they sent us, everything is done. So all we need to do is just run this code and check it. As you can see, everything fits, and in here it says 4.9 times 4.9 newtons, but later found out that E plus O3 just means times 10 to the power 3, which is this is just the same as this but written differently, and also run it up to the 5, I believe. But they just leave it as a more detailed version of it. And see, everything fits. We got theta just means the rad's angular acceleration. So that's just a 3, and I have gotten a 3, and friction and everything fits. But later, and then you ask about, you're wondering that when will there be slipping? So I believe that slipping will occur if the friction force is less than the max friction force. So there will be no slipping, but otherwise if the friction force is greater than the max friction force, there will be slipping. This can be seen when investigating the graph in MATLAB, as seen from here. So no slip assumption is valid as long as the required friction force is less than or equal to the maximum friction force, as seen in this graph. The max friction force right now is this blue line over here, and the current friction force here is just the same. It's just the pretty much acceleration kind of. And then as you can see, when the acceleration is higher than the max friction force, that means that there will be the assumption of no slipping is invalid. This can be seen as we test this through the simulation, as seen here. I just put the friction pretty high, so we can have a more range of the acceleration we can play with. But right now you can see that when the acceleration is low for the truck, when the truck acceleration is low, there will be no slipping. As you can see, this spool is rolling with the width when the truck accelerate. But when you bring the truck acceleration up, there will be slipping, as you can see in this GIF, when the spool just slip off the truck. further proving the graph and my assumption. And thank you for listening to me. And this is just